get started. Uh, any questions before we start today's lecture? General questions about the class?
For the exam, do we get notes or anything on it?
It'll be closed notes.
Okay.
Closed book, closed notes. Yeah. And any other questions about the exam? If you weren't here last lecture, quick announcement, the exam is not next Tuesday but Thursday. So you'll have a chance to look over the homework solutions for homework 5, I guess it is. Okay. And also there's homework 4 going around right now, your homework 4, graded homework 4, so make sure you pick that up today. If you didn't get homework 3, come to office hours and I'll return them to you. Okay. Any other questions?
Yeah, a short question to homework 5. When we are talking about the open loop amplifier, do we have to take into the loading into account, or where do we break up the loop, or just the amplifier itself?
Just the amplifier, yeah. All right, in fact, there's a couple of topics we need to discuss for this homework. And so we're going to go through that fairly quickly, basically because you already are looking at it in your homework, so you probably have read the chapter already in the book or the sections. So we're going to talk about offset voltages and offset currents. And the idea is that if you build an amplifier, say I build a differential amplifier like this, and let's say it's fully differential, and let me ground the input. So I apply 0 differential input voltage, and therefore I would expect to see 0 differential output voltage, but instead I observe some V output differential, right? And so what's going on? Well, it's very easy to understand what's happening. What's the reason that we have offset voltages? Probably you all know by now since you've looked at the homework. So what are some reasons why we have offset voltages in our amplifiers? Okay, mismatches, right? So offset voltages due to mismatch. Various sources of mismatches, right? We know that when we build an amplifier, if it's perfectly symmetric, then if we put in a 0 input voltage, we get 0 output voltage. But if there's any kind of asymmetry in the amplifier, right? two resistors that are supposed to match don't match, or currents in two branches are supposed to match, they don't branch. All these things lead to a systematic offset voltage. Now I say systematic because I want to distinguish between noise that's varying all the time. Of course, if you build 10 amplifiers, they're all going to have different offset voltages, right? Because they're matching. One resistor is going to be too big in one case, and the other case is going to be too small, so it's going to vary all over the place. So the way we model the offset voltage is we assume we have a amplifier with zero offset, and then in series we can put a voltage, VOS. Polarity really doesn't matter because this again is going to be a statistical quantity from part to part. But for a given part, VOS is more or less constant. And so it looks like even though you don't, if I ground the input of my amplifier, there's still a differential input which causes the output to be non-zero. Now it's important, so this is what we call this the offset voltage. And so by definition, it's really input referred. Now let's say I tell you the offset voltage for an amplifier is 10 millivolts. Okay, what is the problem with that? If you're going to now go use this amplifier in different applications, how would this offset voltage affect you? Okay. So let me get you guys started in thinking. Let me make this following argument. This is a DC voltage, right? Who cares? I care about AC voltages, right? And so I'm going to observe the AC differential output. And so the fact that there's this differential offset, I really don't care. You guys buy that? Why not? Vincent, why don't you buy that?
Is it because the gain is big enough and you can ramp it and so you can have enough gain?
Yeah, it's very good. So if this amplifier has a lot of gain, let's say it has a gain of 1,000,000, right? What happens when I put a microvolt on the input? The output swings 1 volt differentially, right? If my supply voltage is 1 volt, then a tiny 1 microvolt input can actually rail the amplifier. What's wrong with railing the amplifier? Well, the gain goes to 0, right? You go outside the range where you actually have gain for your amplifier. What can someone think of other examples where you might be worried about this offset voltage?
DC amplification?
Yeah. So what if you are building a DC amplifier, right? Then you do care about this offset. And let me pose the following question. Is this offset really constant? Is it just a fixed offset? Or would you expect it to vary? I heard something. Anybody? Here's the mic.
Varies with temperature?
Yeah, that's right. As we'll see, this offset voltage has a temperature dependence, right? It's going to be some fraction of overdrive voltage, VT, KT over Q, and so it will vary with temperature. And we'll do a simple calculation today and see how that temperature variation is. But that's a pretty slow variation, right? In terms of, let's say I'm trying to build a system that's just trying to detect either a positive voltage or a negative voltage, right? It's very common. Let's say I'm building a magnetic drive, and I want to read bits off of my drive. And so based on the directional polarization of the bits, I'll either read a positive voltage or a negative voltage. And it's actually a very small voltage. Let's say I build a magnetic coupler and I pick up 1 millivolt signal levels, right? So if it's plus 1 millivolt, that means I recorded at 1. If it's minus 1 millivolt, it means I recorded at 0. So if you're designing that amplifier, first of all, you have to make sure that the integrated noise is much less than a millivolt, right? So you have some SNR. So let's say I've done that. My integrated noise is 50 microvolts, and I'm happy. Now what's the problem? Clearly, now the offset is an issue, because that 1 millivolt signal is not larger than the offset voltage. So it actually can't change the polarity of the output of my amplifier. I need a signal bigger than the offset voltage to actually change the polarity of the output signal. Okay? So clearly this offset voltage is a problem, and there are techniques to deal with it. There's lots of techniques, and we'll talk about them in this class. Incidentally, for some, it's always interesting to get people who don't know the answer to try to guess. What are some techniques that you could try to think of that would deal with this offset? Anything come to mind? Maybe if you know the answer, you could also say it.
Make the input devices larger.
Yeah, I mean, we could always, from a device perspective, go in there and get better matching and pump up the currents or get, bias the thing, and we'll talk about that today. But at some level, you're going to be left with some residual offset. So how do you deal with that?
I mean, for example, some op amps like OP07 uses some resistance they can change off
Yeah.
chip.
Yeah. So we could actually trim the offset. Okay, and let me give you a simple example. Let's say I have a diff pair, and let's just say that the only offsets are these resistors, RC1 and RC2. Because they're not perfectly equal to each other, even though this current, IEE, splits up evenly, there's a residual differential voltage at the output, right? And then divided by the gain, that's the input referred offset voltage. So I could just have another resistor here and adjust its value, right? I can put a screwdriver into my op amp, turn that resistor, that potentiometer, and get exactly the perfect value of resistance so this is matched, right? Is that practical? Well, 1970 it was very practical. Today, of course, this has to be done in some automated fashion. So you want some digital circuit to wake up, measure the offset voltage, and then somehow try to cancel it out. That's perfectly reasonable. Any other things come to mind? How else could you deal with this offset? Anybody have an idea of let's say, a signal processing technique to get rid of the offset? Well, we'll talk about it later. But just for you guys who may be interested, what you could do is, let's say you're trying to amplify a DC signal. Well, you could modulate it up to a higher frequency, go through your amplifier, and modulate it back down, right? You think, oh, that's ridiculous, right? You need two mixers. Now your mixers have to be precise and everything. But do you really need mixers for that? Anybody think of a way of avoiding mixers? So here's the idea. I'm going to basically take my input signal, mix it to some higher frequency, go through my amplifier, and then mix the output back down to a lower frequency. So some of you guys haven't taken 142, so this may not make too much sense. But for those who have, what's a really easy way of implementing these mixers?
You can chop the signal basically with switches, put on, off, on, off.
Yeah, switches. Right, exactly. In fact, you kind of get it for free. Let's say that I had a fully differential amplifier. And what I'd like to do is take my input signal in differential form and kind of multiply it by a waveform which is +1, -1, +1, -1 on the input, and also do the same thing at the output. So how could I achieve that in a very simple way? I could just flip my inputs, right? So one cycle I put my input positive, next cycle I put my input negative. So I just have switches. So I take my positive input and I can either apply it to the positive terminal or the negative terminal, and the same thing for my negative signal. So normally this would go here, this would be phi1, this would be phi2, this would be phi1, or I could take this signal and apply it to the positive terminal. Okay, and this would be phi1. And I can do the same thing at the output, right? And so effectively I've multiplied my signal by plus minus 1 at some frequency we call the chopper rate. This is called chopper stabilization. And we've got to talk about this in more detail, but just to give you an idea of how it works. The nice thing is we have switches on our input anyway, right? So we don't even have to add these switches. If I'm using a switch capacitor circuit, those switches are already there. All I have to do is rewire the switches a little bit, and boom. You might say, well, what happens to the DC voltage? Well, because the transfer function here, if you think about it, if I multiply by plus 1, I get the same thing. Minus 1, I get the same thing, right? So the signal, the net transfer function for the signal, is that it doesn't see this at all. Whereas the transfer function for the offset voltage, which is here, is that it gets modulated only once. And so it actually moves out of the band. So what you're doing is you're modulating the offset voltage out of the DC band where you care about effectively, and it goes away. All right. Let's actually now look at an example. Any questions on this before I move forward? All right, so let's actually do a simple example to calculate what the offset voltage is. And I'll take a really simple topology, let's say a differential pair that we looked at just right now, and let's actually calculate the offset voltage for various quantities that can vary. So for instance, we know that RC could vary, right? We also know that these transistors are not perfectly matched, right? Their dopings could be slightly different. Their geometry could be slightly different. We're just going to lump that all into the saturation current of the devices. So we're going to say that I have, basically I'm going to define an average collector resistance, because they're supposed to be the same, right? And a difference collector resistance. And I can also define an average saturation current and a different saturation current. And we did this before when we looked at matching and, let's say, resistors, so it's the very same concept. And what I'd like to do now is write an expression for the offset voltage. So here's the output. Here's the input. So the observation is that if I take this input voltage, it's basically a difference of VBE. So it's VBE2 minus VBE1. Okay? And I can write VBEs as KT over Q log collector current in device 2 minus the collector current in device 1. And therefore I could say the differential input is KT over Q log IC2 over IC1 plus log IS1 over IS2. Right, so I just, log of the sum is the log of the product, right? So I take the product here and then I write it as a sum again. All right. So now I'm going to say, let's suppose that I actually design my amplifier to have exactly 0 output voltage, right? So I've purposely, so what I've done is I've applied an input voltage so that the output is just 0, okay? So what would that input voltage have to be, right? That's, of course, just the offset voltage. But in terms of this simple circuit, if I've somehow applied an input to make the output equal to 0, what does that imply about this ratio? Okay, somebody says 1. Is that right? Well, it's actually quite simple, because if this voltage is 0, that means this voltage drop is equal to this voltage drop, right? So that means that IC1 RC1 is equal to IC2 RC2. And so if the RCs are different, then the currents are going to be different. So I could say that the ratio of IC1 over IC2 is exactly the ratio of RC1 to RC2. Okay. So I'm going to now write that the offset voltage is KT over Q log of RC1 over RC2 plus log of IS1 over IS2. Okay. And now I can basically start out with these equations and just write RC1 and RC2 in terms of the average quantities, average and difference quantities. So I substitute KT over Q log of, this is, let's say, RC plus delta RC over 2. This is RC minus delta RC over 2. And likewise, this is IS plus delta IS over 2. And this is IS minus delta IS over 2. Okay? And to make things simple, I'm going to assume that this delta is much smaller than the average value, right? Otherwise, nothing will work. So hopefully these are small quantities. So then I write this as KT over Q log of 1 plus delta RC over 2, 1 minus delta RC over 2, plus the same thing here. I won't write it out and bore you guys. And if this is small, right, I can write 1 over 1 plus x as 1 minus x. So then I get log of 1 plus delta RC over 2 times 1 plus delta RC over 2 plus same thing over here. And then I multiply this out, and I get 1 plus delta RC plus delta RC squared over 4. And again, I make the usual assumption that this is a small quantity, so if I square it, it's even going to be smaller. So I drop that small term. And so the offset voltage is KT over Q log of 1 plus delta RC plus log of 1 plus delta RC over delta IS over IS. Okay? And what's log of 1 plus delta, where delta is small? Yeah, it's about delta. So applying that approximation here, then I just get KT over Q delta RC over RC plus delta IS over IS. And this is a simple enough expression that I can stop here. Okay? Any questions or comments about this calculation? All right, well, let's plug in some numbers. So KT over Q is 25 millivolts. And what's a typical matching I might get in resistors? I don't know. Let's say it's 5%. You probably can get better. What's the matching you might get for... Yeah, let's be fair. If this is a bipolar process, and you actually have, let's say, custom thin film resistors, you can... Remember, this is a matching between two resistors which are fabricated nearby. You can get very good precision. You can get 1%. Okay. How about IS? Again, just throw a number at you. Yeah, about 5%. And IS varies a lot more because there's a lot of components in IS. It's just not just like a resistor, right? It just comes down to doping and geometry. With the IS, there's several terms in the transistor, right? There's the actual base doping, there's the base width. Pretty much comes down to geometry and doping too. But with these numbers, again, these are kind of artificial. What do I get? I get 6 times 25, which is 150, so it's 1.5 millivolts. Okay. Now here, I just assumed that these things add together, right? I could have gotten lucky and had subtraction. in which case I would have had 1 millivolt, right? So usually what we do is we assume, let's say I want to know a typical number. As a good engineer, I'm pessimistic, and I say I'm going to assume things at, right? So this will give me a bound on the error. But remember that this number is kind of meaningless. It doesn't mean that you're going to go out and measure every amplifier and you're going to get 1.5 millivolts, right? It could be negative, it could be positive, it could be 0.7, it could be 1. It's going to vary all over the place. It's truly going to be statistical. If I'm interested in the RMS value, right? If I want to know what's basically the standard deviation from the mean, what do? Well, if I assume these are random variables and they're independent, then I could say that the standard variation of the RMS value of the offset voltage is KT over Q squared times the variance of delta RC over RC squared plus delta IS over IS squared. And if we plug in these numbers, so this is 1% squared plus 5% squared. So if I put in 25 millivolts squared, 1% squared plus 5% squared, and I take square root, I get about 1.3 millivolts. So that's interesting. That tells me that the offset voltage is going to vary on the order of a millivolt as I look from part to part, right? So most of the parts will have an offset voltage within this bound of the DC value, right, of the mean value. Okay. All right. The other important thing to observe here is that there's a temperature coefficient, right? And so if I go out and null this offset, just like we talked about before with, like, let's say another resistor, then that will null at one temperature, but not necessarily, it will not track over temperature. That's because the delta IS has temperature dependence, delta RC has temperature dependence, and there's a temperature dependence here. So clearly this will vary with temperature. And if you're in a really high precision application and you can afford it, you'd play with your material properties in such a way that their temperature coefficients canceled out and you can get a very low offset. But we don't really usually design circuits like that. We design circuits for mass production where you can't afford to trim parts individually. Just a note on trimming, a lot of people actually, integrated circuit, right? You can't really vary this resistor with a screwdriver. So how would you vary it? Yeah, you would laser trim it. You'd actually have a bunch of resistors in parallel, and then you would shoot a laser at those resistor contacts and one by one remove resistors until you get the right value of resistance.
What about putting a digital potentiometer in parallel with it and trimming it as you go along with some sort of feedback circuit?
Yeah, that's a more modern way to do it. But again, remember, there's precision involved in your trim circuit, right? So what if your trim circuit has an offset voltage, right? So it's tricky. Okay, what about current offset? Is that going to be important? What would you suspect the sources of current offset would be, in addition to what we've discussed? Well, in the bipolar transistor, the betas, right, don't match. That's kind of well known that you don't know what beta you're going to get. So because of a beta mismatch, you have current offset. So the way we model, in general, the offset of this amplifier is with an offset voltage and an offset current. And so if I voltage drive this thing, meaning I drive it with a low source impedance, then this offset current really doesn't matter, right? Because it just gets shorted. It doesn't go into my amplifier. It's just like noise. We discussed noise. If I drive it with a high impedance, though, then the voltage doesn't matter because it's basically degenerated with a large resistor in series. And so then the offset current dominates. So depending on your application, you may care about offset current or voltage. I was just looking at my notes in the book. There's a factor of 2 here. Not sure why there's a factor of 2 there. Anyhow, you guys can look this up in the book. The reason we don't care too much about offset currents is we use MOS amplifiers, right? And MOS amplifiers, the gate is insulating, and so this offset current is very small. As you scale technology, though, do you guys see a potential problem? Yeah, gate leakage, tunneling current. So 5 years from now, you may be explaining to someone else why there's a factor of 2 here. Today, I don't have to do it. All right, so let's look at MOSFET offset. Again, it's the same game. And I believe you guys have all done this for homework. So we can look at it very briefly, just for completeness. Now, in a real MOSFET amplifier, you don't have resistors here, right? You have a current source, and so then you'd have to calculate the offset in your current source. And I encourage you guys to do that calculation or read through the book. So again, under the trimming conditions, I'm going to assume that ID1 RD1 is equal to ID2 RD2. This is the trim condition. So my differential input voltage is, let's say, M1, M2, VGS1 minus VGS2, which is VT1 plus 2ID1. Again, we're going to use square law because we don't have anything better. Mu C ox W over L minus VT2 minus 2ID2 mu C ox W over L. 1 W over L 2. And just for simplicity, you could argue that T ox is going to vary and mu might vary a little bit. Let's just lump all the variations in W over L. And you can see why I can do that here. Okay, what page am I on? 5. Okay, so the name of the game is to substitute average value, right, plus or minus deviation, average value plus or minus deviation, and then say the deviations are small, and then simplify things to linear terms, right? So therefore the offset voltage is first of all a delta VT, and that actually hurts, right? The fact that the offset voltage is directly proportional to the difference in threshold voltage is one reason that offset voltages in MOS technology are considerably higher than bipolar technology, because threshold voltage vary a lot. Then I'm going to basically factor out the average overdrive voltage, so that's 2ID mu C ox W over L. And then in the parentheses, I'll have the deviations from average. So here I would have 1 minus delta ID over 2ID, 1 minus delta W over L over 2W over L, minus 1 plus, 1 plus, okay, lazy here. And this, of course, is the overdrive voltage for square law. Simplifying this term, right, this is 1 plus x, and so what happens is I get 1 minus delta ID over 2ID, 1 plus delta W over L over 2W over L, minus the same thing, plus minus. And so I can again just keep my linear terms, drop the square term here, the product of two small numbers, and then assume that these are small. So what's square root of 1 plus delta? 1 plus half delta, right? And so then I get half here, and so the answer works out to 1 minus delta ID over 4 ID plus delta W over L over 4 W over L. And you'll notice that I get the same thing out of here. Same exact thing. So I get another term, minus 1 minus delta ID over 4 ID, and also I get another copy of this term. So at the end of the day, the final answer is simply delta VT plus overdrive voltage divided by 2 delta ID over ID minus plus delta W over L over W over L. Okay, and remember, signs don't really matter here. I forgot to include the variations on, I forgot to put in my trim condition, so let me do that. Okay, so basically, it's very easy to show that the trim condition implies that delta ID over ID is just minus delta RD over RD. I'll let you do the algebra to prove that. It's just a couple lines. So that gives me delta VT plus V overdrive over 2 delta RD over RD plus delta W over L over W over L. Okay. Now this is pretty messy, right? By circuit analysis standards. We had to do a lot of messy calculations. You'll notice though that there's nothing magic about this. All I had to, if I had to do this calculation over again and the amplifier were more complicated, instead of keeping all the offsets in one big equation, I would just take them one at a time, right? So I first assume RDs were not matched, and then I would calculate my offset voltage due to RD. Then I would assume W over L is not matched. Then I would assume my current sources are not matched. At the end of the day, they would just all sum up together like this. Okay? Now, is this better or worse than bipolar counterpart? It's worse, right? We already said this term didn't exist for the bipolar transistor. This is actually on the order of millivolts, 10 millivolts. So it's actually a big problem. How about this term? How does this compare? Yeah, I mean, it's a very strong function of layout. Good design, you can get it down to millivolt, sub-millivolt. This term is almost identical, right? Instead of delta IS, I have this delta W over L, which also carries all that baggage with it. Let's say I can get the same precision here. So this works out to, let's say, 4 or 5%, this parentheses. How about this term here? Well, unfortunately, by definition, if I'm in strong inversion region, then my overdrive voltage is basically at least 2 to 3 times KT over Q times N, right? So roughly this is at least N times larger than the case of the bipolar. So this is on the order of hundreds of millivolts as opposed to 25 millivolts. Okay? So MOSFETs have higher offset voltage, but much smaller, for obvious reasons, offset currents. Okay. Now, one thing to point out here is that we're going to use the term random in different ways in this class. We call this the random offset, and the reason we call it a random offset is because it exists because of these delta terms. If deltas were 0, if the circuit were perfectly symmetric, the offset voltage would be equal to 0. A lot of circuits actually have systematic offsets, meaning that by design they are not perfectly symmetric. And if that's the case, there's going to be a systematic offset error. So you have actually a systematic offset plus a random offset, and both come into play. Okay? Now, most circuits that we design, the systematic offset is very small. But I'll give you an example of a... Can someone think of a good example of a systematic offset? I can think of one good one. Anybody out there? It's a good example of a systematic offset.
Differential to single op amps. So you have it two loads while you're taking one out.
Yeah, that was the example I was thinking about. So let's say I have this bipolar input stage, and I have a current mirror. Okay. What is it in particular that's going to be offset by the fact that these loads are not symmetric, right? This guy sees a high impedance load. This guy sees a diode connected load. What will that change? Any guesses? Yes, Debo?
The resistance looking into the source depends upon the drain collector resistance.
So you're saying this current won't split up equally?
Evenly.
Yeah, that's true. Another thing I could think of is because of the early voltage, right? Their currents have to be different because the VCEs are different, right? This one sees a fixed VCE, this one sees a varying VCE. So basically, this circuit is not symmetric. So even if everything matches, there will be a systematic offset in the circuit. Okay. Questions? Okay, so I'm going to change gears now and talk about settling time. In other words, if I'm designing an amplifier, usually I care about the amplifier performing a function like amplification, or maybe an integration or differentiation depending on the application. I want it to perform that function to within some accuracy, right? And that accuracy is determined by the ultimate source, sink of that information, right? If the sink of that information is the human eye, I might say, well, you know, I've done some experiments and I know the human eye is about 1%, you know, sensitivity about 1%. If the image varies around that, no one's going to even tell, right? So if I'm designing an oscilloscope and there's a trace on that oscilloscope, I might say, okay, the accuracy of the function I'm trying to do here, amplification, should be about 1%. Might actually be much more, for the human eye, it might even be 5%, right? On the other hand, if I'm playing music, you know, you might say, okay, now it needs to be 0.1%, right? You can do experiments and have a bunch of people listen to different music, and you can vary basically the accuracy of the samples that, let's say there's a digital source, and you can find the threshold where someone starts to notice that the sound quality is not as good. And it might be 0.1%, right? So ultimately, hopefully we are the sink of this information, right? But there's also intermediate sinks, right? So let's say I'm doing digital signal processing, and the resolution is 10 bits, right? So that means the smallest number is 1 part per thousand, 1 over 10 1024, if you want to be exact. So if my circuit settles within that accuracy, right, of the quantization noise of that converter, then I really don't care. So even though theoretically the settling time for even a single pole system is infinity, right? You have to wait an infinite amount of time until the system settles. In reality, of course, we can stop at some point. And the point we stop is the point where we have enough resolution in our system. All right? Another so usually we call the errors due to settling time dynamic errors, in the sense that depending on how long you wait, you get a different amount of error. What are some other sources of errors and feedback systems that don't depend on time necessarily? Well, a good name would be a static error, right? As opposed to a dynamic error. But where do we get static errors in amplifiers, integrators, other circuits?
Just the gain, if the gain of the open loop isn't the same, or
That's
just not
right.
high enough.
Yeah. So the static errors are due to offset finite gain. Okay. Someone mentioned offset voltage. That's right too. That's something we just talked about. So here's a simple example that you guys have become very familiar with. Say I have a negative inverting stage with feedback capacitor CF, sampling capacitor CS, some parasitic capacitance CP. And if this amplifier has infinite gain, I know that this point will be a virtual ground, right? Basically, this voltage will be this voltage, which is 0, and the entire input voltage gets sampled on this capacitor, and then that charge gets transferred onto this feedback capacitor, and it produces an output voltage, which is exactly minus CS over CF, right? But if this thing has finite gain, let's say AV, the situation is different. So here's the idea. I put a step into my system, and I observe the output. And at the time of the step, let's call this T0, my output, of course, will settle. And even if I wait infinitely long, there will be an error. This is the static error that we're interested in. So has nothing to do with how long you wait, right? Because if I stop here, clearly there's going to be a huge error, but that means you just didn't wait long enough. Wait long enough, and then you will, at the very end, still observe some error. Okay? So how do we find this error? Well, we just analyze the circuit. It's pretty simple. Let's do KCL at this node. So I would have Vx minus Vn SCS plus Vx SC plot CP, parasitic, plus Vx minus Vo SCF is equal to 0. And let's say at the, so let me just write this as Vx CS plus CP plus CF is equal to the input voltage times SCS. Well, S really cancels out, so I can get rid of it. Plus V out over CF. Okay. So now I have an equation that says Vx is feedback factor F times VO, where F is defined like before as CF over CS plus CP plus CF. This is just the total capacitance, plus feedback factor times CS over CF times V in. Okay. Questions? Pretty clear? Good. Well, if this is a high gain amplifier, what's Vx? Well, if it's very high gain, it's 0, right? And then in which case V out would be exactly equal to minus CS over CF times V in. If the gain is finite, though, what's Vx going to be? Yeah, it's going to be VO minus VO divided by the gain. Minus because this is the minus terminal. So that's the defining equation. Let me divide everything by F here. And so you can really now see that this is the error term. This is the origin of the error term. Okay. Okay, so let's see what happens if we now keep this error term around. Well, again, I won't bore you by doing elementary school algebra. Our final equation works out to something you've probably seen before. The output over the input is the actual ideal gain, let's call that C, divided by 1 plus 1 over AVF, which is what? It's a loop gain, right? T, loop gain. And if my loop gain is very large, then 1 over the loop gain is very small, so this is approximately C, 1 minus 1 over the loop gain. Okay? And so this is in fact my relative error. This is the static error. Now there's actually a couple of really interesting things in this equation. Looking at this equation, how should I calculate my loop gain? Is this a small signal gain or a large signal gain? Okay, Shiji, why is it a large signal gain?
When we develop an equation, we actually use the V naught divided by open loop gain. So V naught is a large signal divided by open. So that's
Yeah, if you go back and look at this analysis, nowhere did we make a small signal approximation, right? So really, this is V out over V in. AV is V out over Vx. It's not dV out over dVx. This is, so AV is the large signal gain. And now you can see why we care about the large signal gain, because ultimately how much gain we need in an amplifier is determined by how much accuracy we need, right? So let's say I want, let's do a simple example. So let's say that I want to design an amplifier with a closed loop gain of -4, which we called C. And let's say in this particular problem, I use a 1 picofarad feedback capacitor, 4 picofarad sampling capacitor, and I end up with 1 picofarad of CGS capacitance. How do I size these capacitors, incidentally? Is this arbitrary? Why not use tiny, tiny capacitors? Well, think about what you've learned. Don't think about something you haven't learned yet. How do you determine how to size capacitors? And noise, right? You guys all know this, right? So noise determines how we size these capacitors. So let's say in this system, this is the level of capacitance I need to meet the noise specs, okay? Now I calculate this factor F, and F in this case, we've defined it as CF over the total capacitance. So it's equal to 1 over 6. Now, this is really important that F is not equal to 1 over the closed loop gain, right? 1 over the closed loop gain is 4, 1 over 4. Here, F is 1 over 6. So this capacitance CP actually will hurt us. Okay? That's something important to take into account. So now let's say our spec is to have an error of less than 0.1%. Okay? So that's very simple. Our error is just fraction 1 over 8. Basically, this is our error. It's the loop gain, 1 over the loop gain. So in other words, the loop gain should be greater than, what is that, 1,000, right? And because F is 1/6, the gain should be bigger than 6,000. And this gain should be maintained over the desired output range. So now you get to see why this output swing is so important, and specifically why the gain over that output swing is very important. Because if I were designing this amplifier, I would, let's say I were speccing it and giving it to you to design. I would say, okay, I need a 1 volt swing at the output, and over that swing you got to give me a gain of 6,000 because I need to hit 0.1% static error specifications. So then you're going to go design your op amp, and then you're going to plot its large signal gain as you vary the output voltage, right? And you want to make sure that the gain is above 6,000 over process and temperature over a swing of 1 volt. If you do that, you're set. Okay? You have a question?
Could you explain that portion a little bit? F not equal to 1 over C, what you said.
Okay, so the idea is that in this amplifier, the gain, the closed loop gain, does not depend on CP. Closed loop gain is just minus CS over CF. Okay? But in doing this calculation, and in fact we saw this for the noise as well, this factor F is important. And F is a function of CP. Okay? So this capacitance on this negative terminal may seem negligible to you, right? You might say, this is a virtual ground. I don't care what capacitance I have here. But when you design the amplifier, you find that the static gain error is actually worse than you predicted. Why? Because you didn't include the CGS of this input transistor. Okay. Same argument goes for noise. You guys we saw that a few lectures back. Okay, well, if I were going after a 0.1% spec, would 6,000 be enough?
No.
Why not?
I think there are some other noise, and also some when we need a switch, and switch inject some
Okay.
noise too.
Yeah, there's lots of other sources of errors we haven't even started talking about, right? So if your total goal is 0.1%, you've got to split that error between all the various mechanisms that you know about. And so you have a budget, basically. And this is kind of where the design decision comes from. How much of the error do you let go to your static error? Well, in the old days when you're designing with long channel transistors, gain was very easy to come by. Oh, gain a million, no problem. Nowadays, though, short channel devices, it's pretty hard to get a gain out of single stage. The single stage gain might be 5 or 10. So to get a gain of 1,000, you're going to need a lot of stages or gain boosting. You're going to have to play some tricks. So getting gain is not easy. So you might actually decide that you're going to eat up a lot of your error budget with just this gain error and make everything else fast, right? Because the other source of the error is a dynamic error, which depends on the speed of your circuit. So that's an important trade-off. All right, so let's now look at the dynamic errors. And we'll start out with just a very, very simple model of our amp and look at its linear settling behavior. So again, here's the model of the amp. And I want to know how does, I'm going to put a load here, CL, CF, CP, CS. And the question is, if I apply a step at the input, what's the how does the output settle? What are the settling characteristics? Well, you guys know, let's say that this is a GM generator. You guys already know that you're going to get a dominant pole, right? GM over CL. In fact, it's CL effective because you do see a fraction of your feedback capacitor. So that's going to be the dominant pole of your system. What are some other sources of poles and zeros in this circuit? A simple question. Right. Not a trick question. Okay, CF gives you a 0. Yeah, so basically we have a feed-forward 0. What else?
In the input node, and we have a mirror effect on the CF.
Yeah, but at the input node, right, that just adds to these capacitors. Does it really hurt us? Let's say I voltage drive this. Any other poles or zeros in the circuit that... So you go and build this transconductor, right? Obviously you're going to get a pole out of that, right? So GM stage has its own poles and zeros. Okay? So these are, basically we get a dominant pole from CL, and then these poles are what we call the non-dominant poles. Right? These are the poles of the internal amplifier. That's why I said it's not a trick question. You guys all knew the answer. Okay, the feed-forward 0 is actually interesting because, as we've talked about previously, it does the exact wrong thing, right? If I put a step on the input, then what happens initially at the output? It also steps up, right? With, let's say, a smaller magnitude. What determines the magnitude? Yeah, cap divider, right? So I've got this capacitive network. At the very instant of the step, because this amplifier has finite bandwidth, it can't do anything. So at that instant, the amplifier is not even there, and this is just a simple passive capacitive network. So I can calculate exactly what this step does. Well, once the amplifier wakes up, what does it do? Well, it sees that there's an error voltage at the input, and feedback, right, will drive that error voltage to a small value. In fact, because the output has gone in the opposite direction, right, this is an inverting amplifier, so the final value is somewhere over here, where this is 0. So the first thing the amplifier does is it actually corrects for the feed forward. And then it settles to the final value. So this effect of the 0 apparently may be important. It's something we should try to take into account when we do our analysis. So for that reason, and that reason alone, instead of just saying there's one pole GM over CL and then other poles and zeros are due to the GM, let's analyze this circuit carefully to find exactly the location of that pole and that 0. So again, I'm going to just write KCL here. Let's call this node Vx. In fact, we just wrote this equation. So what do we get? We got Vx CS plus CP plus CF. That's the total capacitance on this node, is equal to Vin CS plus VO CF. And we just wrote this as CS over CF times F times Vin plus F times VO. Right? That was derived on the previous page. Now on the output, things are a little bit different because I have this transconductance. So on the output, I have the current through this load capacitance plus the current through this GM, right, which is a function of Vx, plus the feedback current, which is Vout minus Vx SCF. Okay. In other words, Vout, by group terms here, is CL plus CF, which is equal to Vx, which is SCF minus GM. Okay. And now I just substitute for Vx here. And again, I'm not going to bore you guys with algebra. If you do this carefully, I know you guys will all get the right answer when you make the substitution. And this is the final answer. So the small signal transfer function is CS over CF, F, SCF minus GM, FGM plus SCL plus CF, 1 minus F. Okay, and I'm writing it in this form to kind of make a point. All right, that's the right answer. Okay, but if you put that on an exam, you probably will not get full credit. Okay, what's wrong with this answer? Yeah, it's kind of ugly, right? You know, there is aesthetics. If anyone tells you, oh, engineering, it's all about just getting the right answer. No, there's aesthetics. If I look at this, it doesn't tell me anything. I want to put this equation in a form where every term is clear, right? So what do I do? Well, let me factor out a GM from the numerator. So then I would have, and put a negative sign here, so I'd have 1 minus SCF over GM. On the denominator, I'm going to factor out an FGM. So this is 1 plus S CL CF 1 minus F over FGM. Okay, and the FGMs cancel, and I get this term, which is the ideal gain, right, times 1 minus, let's say, S over Z, and 1 plus S over P. And because I like to have my, oh yeah, that's fine, I'll leave it in that form. Okay, so now this equation is clean, and I write that my 0 is GM over CF, and my pole is FGM over CL plus CF 1 minus F. So then I look at my pole and 0 and say, do these make sense? Does it make sense that at a frequency GM over CF I'd have a 0? Right? You check your answer. I mean, in this case it's so simple that you can check it. Make sure you didn't make any algebraic errors.
Yeah, question. Actually, GM has some like frequency because GM itself has zeros and poles. So
Yeah, you're absolutely right. But what we're going to do now is make a simplifying assumption that GM is constant. Okay. By looking at this equation, does it make sense that there should be a 0 at frequency GM over CF? Well, yeah, because there's two paths to the output. There's the 0 path, and then there's the GM path. And at this frequency, right, the current going through CF is actually GM times the input voltage, which is the same as the GM path, but with opposite phase. So they cancel each other, and the transfer function has a 0 in it, right? What about the pole? Does the pole make sense? So I might write this as FGM over CL effective. So first of all, does it make sense that the pole frequency is F times GM over CL effective, based on your background and frequency response of feedback amplifiers, right? Yes, it makes perfect sense, right? GM over CL effective, that's the unity gain frequency, right? Homework number 2 or 1, you guys calculated unity gain frequency. And if I apply feedback, the bandwidth should improve by the loop gain, right? So yeah, this makes perfect sense. So I'm applying feedback here so that my gain, instead of being what it is of the amplifier, it's 1 over F, and so my bandwidth should improve by exactly 1 over F, which is F. So the bandwidth is F times the unity gain bandwidth. How about CL effective? Does this make sense? Anybody want to comment on the form of CL effective? Why isn't it just CL? Okay. Let's get somebody from the left-hand side to keep the number of answers balanced. It's like a chopper, right? That way I can make the offset equal to 0. Right now there's an offset in this side. You guys have to do your fair share. Okay, Mariam, you're up. Does this look reasonable to you? Yeah, very good. Perfect. See? All you have to do is volunteer and take a chance, right? Intuition is very important. You know, you said it reminds me of the Miller effect. Perfect. You're probably right. So what do you do next is you check it. I have a capacitor CF. What's the gain from the terminal Vx to Vout? Well, in a closed loop, it's just 1 over F, right? So then this is equivalent to a capacitance, let's say C1, and a capacitance C2. C1 is CF 1 minus AV, right? This is actually negative. C2 is CF 1 minus 1 over AV, right? So that would be CF 1 plus 1 over F, and this would be CF 1 minus F. Perfect. So this is in fact the Miller cap. So if I look at my circuit, then it becomes very clear that the load is CL plus this capacitance Miller multiplied, which is just 1 minus CF. Okay, so now that the answer is in a form that I like, I can look at my step response. Okay, so my transfer function is C 1 minus S over Z 1 plus S over P. So I have a left half plane pole and a right half plane 0. And the output voltage, of course, is just the inverse transform of H of S times the input, which is a step function. Let's say it's V in over S. 1 over S because it's a step function. And you guys all know how to do this calculation. The output in time is the input voltage times C, that's the gain. Say C here is negative, times the settling term. And basically, if you do a partial fraction expansion of this, right, you get 2 terms, and at the end of the day, this is the final answer that you get. All right, not too surprising. This is your error term, let's say. So this is our dynamic error term. If you wait infinitely long, what happens to the error? Let's say this is the error term here. Oh, it goes away because this pole is in the negative left half plane, right? It's in the left half plane. So if I wait infinitely long, this term goes to 0 and I have no error. So looking at this equation, can anyone tell me a good strategy for picking your poles and zeros? First of all, let's look at this time constant. So the time constant is 1 over P, which is in fact exactly what you think it should be. It's your effective capacitance divided by F times GM. It's just the bandwidth of the circuit. So it's a single pole system. Of course, the bandwidth is just going to be equal to basically the pole frequency. And the settling time is going to be 1 over that pole frequency. But let's say I gave this to you guys and I said, go and make this amplifier as fast as you can. How would you choose your poles and zeros? First of all, let me give you a hint. Where's the pole and where's the zero? One's in the left half plane, one's the right half plane, right? So in fact, this is 1 minus absolute value of P over Z. Okay? Anybody want to tell me the best solution? Make it the same. Okay? Does anybody buy that? Is that a good answer? What would be the bandwidth if I made the pole and the zero the same? What would it be? Yeah, I would have infinite bandwidth, right? What's wrong with having infinite bandwidth? I'll buy that, right? Is it physical? Can you get infinite bandwidth out of this system? Why not? We just did the math, right? The math says that if I make P is equal to 0, this term goes to 0. It settles infinitely fast. There is no settling time. Okay, Debo, you want to use a mic?
You can consider the non-dominant poles still.
Let's say that, let's forget those for now, right? Okay, that's fine. If you consider non-dominant poles, then the bandwidth will be set by your non-dominant pole, which is like on the order of ft, which is really fast. So okay, I don't get infinite bandwidth, but I get, let's say, 10 gigahertz, 20 gigahertz. Is that physical? Okay.
The slewing rate of an op-amp.
Okay, that's very good. You guys, how many guys studied slewing in 140? Okay, talk about that probably next lecture. But yeah, there's nonlinear effects, right? This is a linear model. Linear model predicts that you have infinite bandwidth. I'm going to stick with my linear model. I'm going to say, look, I'm going to make sure my signals are small enough so that slewing doesn't happen. And you'll see that that's possible next lecture, so that my linear model is still valid. Do I get infinite bandwidth out? Okay. David, what do you think? What's your gut instinct telling you? I'll use the mic.
You shouldn't be able to get infinite bandwidth.
No, it's not infinite. It's going to be, as pointed out, the non-dominant pole. What's wrong with that? Okay, here's the surprising answer is, yes, you can do this, and it does work. You can make your pole equal to your zero, and in fact, you guys are all familiar with the system that does this. Anybody remember? Think about it when you're in the lab. When you're in the lab, you use this technique. What do you use it on? Imagine like the first electronics lab you took, right? What measurement did you do? Okay, if you use an oscilloscope, what's the first thing you do on an oscilloscope? How many people have used an oscilloscope? All right. So let's say you look at your oscilloscope, and on the trace, have you ever noticed an oscilloscope looks like it's a very high bandwidth system? Did it ever surprise you that if you put a step function on your oscilloscope and it's properly balanced, you get a step function on the output? How is that achievable, right? The op-amp's got to be made with electronics. You know, that perfect step function, where is it coming from? Right? In fact, if you first hook up your op-amp and you see something like this, your probe has a little place where you could put a screwdriver, right? What are you doing when you change that value of that capacitance? Well, actually, you're creating a zero, and you change it until you see a perfect step function, right? At that point, you've created a zero, which cancels the pole, and in fact, you get a very high bandwidth. Pretty cool, right? What's wrong with this approach? Why don't we all use it? Why is this news to you guys? You know, why is it that every amplifier doesn't use this technique? Okay, the claim is we are using it. Miller compensation. Miller's a little bit different, right? Yeah, so that's something that we'll talk about. Yeah, so we do use it, but what's the problem? If I'm going to design an amplifier, how do I make P over Z equal to 1? In fact, what is P over Z? Let's write it out. So P over Z is minus F CF over CL effective. Okay? And this has to be precisely minus 1. Is that achievable? Well, what if your load capacitance varies by 5%, right? The problem is that you're never going to get perfect locations for your pole and zero, right? Or this is not pole zero cancellation. This is a pole here and a zero here. So that at any point on the j omega axis, my distance from the pole is the same as my distance from the zero, so it doesn't ever hurt me to see the pole. Well, what if this is slightly offset, right? Then, if this is slightly offset, these distances are not exactly the same, and I actually will feel the effect of my pole zero. So the idea is that if I go back and look at this equation, if these are minus 1 plus epsilon, right? So let's assume that V out of t is minus V in C, 1 minus P over Z. Let's call that 1 plus epsilon. Whoops, times e to the pt. Then you can see this 1 cancels out, and I end up with getting 1 minus epsilon e to the pt. Well, that's great, but I still now have to wait. So if epsilon turns out to be bigger than the settling accuracy that I want, then I have to still wait the same amount of time until that epsilon times e to the pt is small enough, right? So let's say that through a really great layout, I make epsilon 1%. And I'm really proud. I go around telling everybody I managed to get my pole and zero down accurate to 1%. Well, if you're designing a scope, the human eye is not going to see a percent. So even though this term is still there, you just don't perceive it. So on the trace, it looks like a perfect step function. But now you try to sell this to your customer, and your customer says, no, I want 0.1%. It's hopeless. You're never going to get 0.1%. So then you're going to have to wait. Okay, we'll pick that up next lecture.